under the ocean tonight, a submarine fiber-optic cable is carrying light. It rests on the seabed in the cold dark, and a small signal begins much nearer to you. This is the Night Almanac, your home in the dark, with nothing to do and nowhere to be. Tonight you drift far out, past the room, past the city, to where the world goes quiet, and home by morning. Sleep whenever you like. For a moment, the room is only fabric, wood, and a muted bedside glow. The connection beside you seems almost weightless. Nothing in its quiet appearance suggests a path that reaches past walls, streets, and the last dry ground. You hear no distance in it. The room keeps its familiar proportions as the passage begins. The first part is almost too ordinary to notice. A short indoor path leads away from the place where you rest, disappearing into the structure of the house. The signal does not need a grand departure. It only needs the next handoff. A message leaves the bedside connection and passes through the house. It does not yet meet salt, surf, or pressure. It simply moves outward from a familiar room into the terrestrial network that serves the land. At the outer wall, the domestic scale ends. The path is no longer measured by the width of a room or the length of a hallway. It joins a larger network on dry ground, where the house becomes only one quiet origin among many. Behind you are bedding, plaster, and wood. Ahead, the buried course turns coastward. At the coast, the path is simple, as public guidance from the International Cable Protection Committee describes it. From the ocean, a submarine fiber-optic cable reaches a beach manhole, passes into a landing station, and connects there to the terrestrial network. Seen from home, you follow that same sequence in reverse, moving toward dry land's edge. That reversal gives the coast a different shape. You do not start with a vessel or a distant horizon. You begin inland, tracing the prepared way toward a covered opening in the beach. The sea is the final side of the threshold, not the first. Distance widens while the visible scale narrows. Houses recede, the ground opens, and the coastal building remains low against the sky. The path is not visible from the pillow. It is hidden inside ordinary walls, then carried away across the settled ground. The signal has no view of roofs or gardens. It only continues along the prepared path that leads toward the shore. Soon the house leaves the visual field, and a wider coastal sky takes its place. Whether you send an email, make an airline booking, or telephone overseas, there is more than a 95% probability that the action involves the International Submarine Cable Network. The examples are everyday ones, yet their path reaches a dark margin far beyond the room. The objects remain simple after you know this. A closed computer is still a dark rectangle. A telephone still fits on a table. The scale changes only in your attention as the ordinary action acquires a coast, a shore entrance, and a long submerged continuation. Outside the house, the distance begins to feel larger. Buildings give way slowly, one block after another, while the terrestrial network continues toward the coast. There is no single dramatic border. Dry ground simply narrows until the smell of salt and the open horizon belong to the same direction. The inland section approaches its last few changes. Pavement becomes a service track. The view opens around the course. Low vegetation bends near the dunes, and the station remains a modest shape rather than a landmark. You advance without leaving the prepared path. The ground carries you closer to the place where terrestrial equipment meets the shore approach. Nothing here resembles the distant, deep sea. The surroundings are still sand, grass, concrete, and sealed access points. You come nearer to the beach through the inland side of the course. The signal approaches from behind the dunes rather than from the sea. Ahead, the buried passage has to cross a threshold where streets, sand, tide, and engineered shelter meet within a short span. The beach manhole sits low and practical, a covered access point at the coast. Around it, grains collect in shallow rims. The lid does not announce the distance carried beneath it. It belongs to the shore as quietly as a drain cover or a weathered stone. From standing height, the access point nearly disappears within the broad, uneven beach. Metal meets packed grains, while the protected way remains enclosed beneath the open shore. Here, the landward track reaches its coastal threshold. The conduit passes below the beach surface and into the protected opening. Above, the tide advances and withdraws. Below, the prepared passage turns toward the building that receives the system on dry ground. You pass the manhole without lingering. The signal is handed onward through the shore approach, leaving the open beach for the landing station. Its next surroundings are enclosed: walls, floors, cabinets, insulated leads, and equipment arranged around the protected passage. Wind-shaped sand ends at a firm threshold, and the open sky gives way to a ceiling. Inside, the passage is easier to contain visually. It enters through protected openings, crosses no public room, and belongs immediately to the equipment space. The beach remains close outside, but the building turns attention inward toward cabinets and insulated connections. Power feeding equipment is often installed in a landing station near a coast, separate from urban optical terminal sites. The coastal building, therefore, keeps one essential function close to the sea, while other terminal work may remain farther inland. Inside, the station becomes a sequence of fixed surfaces. The floor is clear, the cabinet doors are closed, and the protected strand turns through the room without exposing what travels within. You notice how little the enclosure resembles the scale of the distant passage. The ceiling is reachable, the aisle is narrow, and each cabinet has a definite edge. Beyond this compact interior, the submerged corridor will extend far outside any single field of view. The station gathers a vast distance into a few physical contacts. A strand enters. A lead departs. Closed panels stand between them. The whole coastward handoff is held inside a space that could be crossed in a few slow steps. You enter the equipment room through a quiet threshold. Nothing needs to move across the floor. The work is contained inside cabinets and conductors, and the important action remains hidden behind fixed metal surfaces. Then the small find becomes clear. Power feeding equipment at the landing station supplies constant direct current to the submerged repeaters along the submarine cable system. Not a message, but a steady current sent seaward so distant machines can keep their work. After that, the passage turns physical again. A protected connection leaves the cabinet and bends toward the seaward side of the building. The source remains enclosed and ordinary-looking, while the outward approach disappears through a sealed floor opening. You follow the lead to the wall, where the station releases it toward sand. A typical optical submarine system configuration includes land wavelength division multiplexing equipment, submarine repeaters that amplify optical signals, power feeding equipment for those repeaters, and monitoring equipment. The land multiplexing gear combines many colors of light into the fiber. You move past the inventory as the work advances. Cabinets stand in rows, each closed face giving little away. Narrow seams, floor openings, and overhead trays guide your attention toward the seaward end of the room. The many functions do not need to look alike. Some connections are fine and carefully routed. Others are thickly insulated. The cabinets give each task its own enclosure, so the room reads as a sequence of surfaces, gaps, corners, and turning paths. At the aisle's end, sealed exits turn seaward through a blank station wall. NEC describes long-distance systems as needing a maximum power feed voltage around 15,000 volts. The figure belongs to the reach of the system, not to any visible flash in the room. You see only insulation, separation, and a carefully contained run. The number passes, and the span narrows again. From the scale of a station, you return to the physical strand that must leave the building. It is thin compared with the rooms that serve it, yet the entire seaward thread depends on that modest object remaining continuous. Seen close, the strand occupies little space beside the conduit that protects its passage. The wall, floor, and cabinet all seem oversized around it. This contrast stays with you as the course turns back toward the beach. The building has served as a sheltered crossing point. Now, the physical passage must leave the controlled room and accept the shifting surfaces outside. The handoff is quiet. Enclosure to buried approach, fixed floor to coastal ground. At the seaward wall, the protected connection bends toward the beach. The building is now behind you in function, though still close in distance. Ahead lies compacted ground, then sand darkened by the tide, then the shallow shelf where burial can begin. Outside again, the station door closes from the scene without ceremony. The building becomes a low shape among dunes, while the way holds to the ground. Your view stretches forward across rough grass, pale sand, and a broad band of reflected sky. The signal passes from cabinet to conduit, from enclosure to buried approach. Each handoff removes another familiar surface. Metal doors give way to soil. Ground yields to wet sand. The shore becomes less like a boundary and more like a gradual change in what covers the track. You move across that transition without stepping back into the station. The building remains behind the dunes, close enough to belong to the coast, yet already absent from the immediate scene. Ahead, the wet margin reflects a pale sky. At the edge of the tide, the strand enters another kind of concealment. Sand lies above it, then a shallow, moving surface, then the seabed beyond. The strand continues through these layers without becoming visible from shore. You reach the open beach again, but now from below its surface. The manhole is behind the direction of travel. The landing station has already done its part. Near the surf, the strand continues under a protective course chosen for the exposed shallows. Telecommunications, submarine cables are small in diameter and can be surface laid or buried, typically to about 1.5 meters where feasible, to protect the cable from external aggression. Near the coast, burial places the narrow conduit below the active surface of the seabed. The corridor now belongs to the broad shallows. Sand and sediment occupy the frame, while the coast begins to recede behind the seaward direction. The scale widens again. The strand rests against an expansive pale shelf. Near the bottom, the shore is no longer a collection of separate objects. The access cover, concrete walls, and cabinet aisles have disappeared from view. Only a distant brightness suggests land, while the foreground is made of sediment, shadow, and the approaching plow. You keep near the strand as it approaches the burial work. It does not wander across the bottom. Its direction is held toward the place where the plow waits, low and heavy against the pale sediment. The nearshore shelf receives the strand gradually. Behind you, the last structures lose their detail. Farther out, the seabed stretches with fewer signs from land. The strand nears the pale surface under control. A sea plow provides the most effective burial method described. As a cable approaches the seabed, it is fed through the plow, which inserts the cable into a narrow furrow. The share opens the ground, the strand goes down, and the sand closes. The oldest idea, done underwater, at the speed of a slow walk. Behind the machine, the recent passage leaves a fresh mark across pale sediment. From farther back, the tool occupies only a small part of the shelf. The surrounding seabed remains broad, with the new groove running away from the shore. You follow the fresh track at an unhurried pace. Near the machine, the groove remains distinct. Farther back, its edges soften into the surrounding sediment, and the track leads away from the beach. The station now recedes into the dry coast. The approach no longer needs the room as a setting. The dunes and surf have been crossed, and what remains nearby is sediment with the faint trace of recent burial. The coast is still there when you look back, but it has lost its detail. No cabinet can be distinguished. No access cover can be found. The shore has become a pale horizontal presence above the shelf. The furrow continues for a while, then becomes difficult to distinguish from the surrounding seabed. A slight change in texture is enough. Above it, the shallow sea moves without revealing the object below. The strand keeps its place under the softened surface. Beyond the last fixed room, the built coast withdraws and the seabed opens onward. The sea plow continues ahead until the nearshore work belongs to the past. Its furrow carries the thin physical run into deeper, darker ground. Behind it, the coast is still present, but now peripheral, reduced to a pale band above the seabed. The longer shelf passage lies ahead, broad and unlit. The landing station and the first protective burial remain behind you, while the buried strand proceeds seaward beneath the cold dark. You rise away from the coastal station and look down across the pale shelf, where the buried strand leaves the beach behind and enters open water. Nearshore sand spreads beneath a thin blue veil, then loses the sharp marks of the recent plowing as the vessel moves farther out. The landing remains visible only as part of the low coast, while the surveyed route takes over the view and leads toward a broader, unlit expanse. Below the hull, pale grains blur into a continuous field. The nearshore furrow is already fading from sight. From the stern, the shore seems to flatten as distance gathers. The beach becomes a pale seam between land and sea, then loses the separate details that mattered during the landing. Below the wake, the route continues outward with no visible interruption, linking the buried approach to the open shelf, while the vessel draws steadily away from the place where the work began. A preliminary desktop study assembles hydrographic and geologic information, and typically includes visits to landings to determine where the cable crosses the beach and links to the cable terminal, onshore ground, coastal sediment, and the first offshore reach are considered together before the work proceeds seaward. So the path now passing below the hull begins with observations made at both sides of the surf. That early preparation recedes with the shoreline. Beneath you, the floor no longer looks like the narrow strip approached from land. It opens into a field whose small variations matter across a much greater distance. Pale patches merge with darker sediment, and soft ridges run obliquely under the course. The ship follows a selected corridor through those changing textures without turning the seaward passage into a series of abrupt corrections. The first survey swaths lie across the shelf like overlapping views rather than marks painted on the bottom. Each pass gathers another portion of the surface, joining shallow ground near the beach to the descending region ahead. Seen from above, the wake is narrow and temporary. Below, the examined area is broad enough to show where the course may continue and where nearby terrain differs from the chosen track. A cable route survey commonly covers a swath of seabed about 1 kilometer wide in depths down to about 1,500 meters, reflecting the need to bury cables for protection according to local conditions. That breadth gives the planned course room to pass through suitable ground instead of depending on a single narrow trace. And the pale corridor below seems wider than the vessel that now occupies only a small part of it. Near the center of the examined band, the sediment has a subdued, continuous appearance. Toward its sides, darker patches and low, uneven ground become more frequent, giving the chosen course a physical setting rather than an invisible abstraction. The ship stays over the smoother reach, and the distance to either margin is expressed only by the slow spread of changing texture beneath the blue. You remain within that known band as the nearshore gradient eases. Fine sediment forms long, subdued stretches, interrupted by areas whose grain and relief appear different even in the weak light. The selected path keeps moving outward through the center of the observed ground. Behind the stern, the coast has become a thin, horizontal shape, while ahead the shelf continues with no built structure or bright marker to define its scale. Multi-beam systems provide full depth coverage of a swath of seabed with a width that is 3 to 5 times the water depth, rather than a single line under the ship. The system therefore records a broad area beneath each pass, and the hull advances over a floor understood across its breadth, instead of only along the narrow center, directly below the keel. The underside of the ship passes over the shelf as a dark, temporary shape. Far below, the ground remains fully exposed in broad contours, with no single central groove defining what has been observed. A shallow depression opens to one side and closes again behind, while the selected route holds across the more gradual surface ahead. measured field widens around the moving track. Low rises, shallow hollows, and gradual slopes belong to one continuous surface, so their relation can be followed across the route rather than encountered as isolated features. You look down through cold blue space at a shelf that is beginning to tilt, its broad form revealed not by a visible boundary, but by the slow change in distance between vessel and bottom. In deep water, a single multi-beam track can be up to 20 kilometers wide. Farther out, one pass may therefore cover an immense breadth below the ship, where the darkened floor extends beyond the reach of any ordinary downward glance, and the surface wake remains only a slim pale seam above it. At this scale, the hull becomes a small moving point above a field too broad to take in from its deck. The surveyed ground extends far beyond the wake, joining slopes and flatter areas within the same offshore reach. You stay with the narrow course through that breadth, where direction comes from the planned passage rather than from any visible edge. That larger reach carries the route beyond the visual scale of the beach. The shelf still descends gradually, yet its edges no longer belong to the same view. Only the chosen course gives direction through the open expanse. A muted band of lighter sediment passes beneath the keel, then fades into deeper blue as the ship proceeds toward ground that feels flatter, darker, and more remote from the coast. Before the descent becomes pronounced, the surveyed surface shows another kind of detail. Broad coverage establishes shape, but texture appears through differences in tone, roughness, and shadow. The route approaches patches where stone interrupts sediment, then passes ridged sand whose crests lie across the floor. Nothing moves quickly in this view. The changes arrive by degrees as the hull carries you over them. Side-scan sonar can produce photographic-like images of the seabed surface, used to identify rock, gravel, sand waves, shipwrecks, and other cables. These features appear through the character of their surfaces and shadows, allowing the proposed course to be examined against objects and textures that may cross it or lie nearby. The vessel moves on, and each surface leaves a different kind of trace in the dim field. Coarse ground breaks the light into small hard patches. Smoother areas hold longer tones. Raised forms produce narrow shadows beside their crests. The route proceeds through this sequence without pausing over any object, using the observed character of the floor to keep the offshore course clear. You pass above a hard, broken patch, then over finer ground where the ridges become longer and more regular. A wreck shape remains off the selected corridor, dim and still, while an older strand lies elsewhere on the floor without drawing the new route toward it. The vessel continues across the observed band, carrying the fresh length along a path chosen through those physical traces rather than through empty blue. The stony textures fall behind, Ahead, the surface becomes more uniform, and the furrow from protective burial runs across it as a narrow disturbance in otherwise muted sediment. The mark does not remain equally clear at every distance. Nearby, it has edges and displaced grains, while farther back, it blends into the shelf. You follow its direction seaward, where the pale upper ground begins a long descent. Cables that extend across the continental shelf to roughly 1,000 meters to 1,500 meters of water depth are commonly buried below the seabed to protect them from damage by other seabed users. The protective track, therefore, continues far from shore, where local conditions require it, leaving a subdued groove across the descending slope before the placed length disappears beneath the upper layer. Behind the plow, disturbed grains settle into a narrow band. The buried course is no longer visible as an exposed strand, yet the recent passage remains apparent in the altered surface, which runs straight through the cold blue distance. The vessel moves above that trace, while the terrain lowers gradually, and the last nearshore brightness thins until the floor carries only a faint gray cast. The upper slope passes slowly under the hull. A narrow, altered band remains visible for a time, then becomes harder to distinguish as distance and darkness reduce the contrast. The surrounding floor keeps its broad, pale gray tone, and the route points directly toward the place where the seabed drops farther from the machinery above. The burial reach gives way as the course approaches deeper ground. Below the stern, the conduit begins to leave the machinery and hang freely before meeting the floor. Its curve lengthens into the darker space behind the ship, supported at one end by the handling gear and drawn downward at the other by the increasing separation from the seabed. You stay with that suspended curve as it grows broader. The upper portion follows the stern, while the lower part sinks toward the slope without dropping vertically. Forward movement shapes the length into a smooth bend, and the seabed rises slowly into clearer view beneath it. Between hull and sediment, the route is briefly held in open blue, neither stored aboard nor yet resting below. The lowest curve approaches the floor by degrees. Fine grains show more clearly under the descending length, and small relief on the slope gives the meeting place a physical surface rather than an abstract depth. There is no sharp plunge in the motion. The gap simply narrows as the ship continues until the suspended part begins to transfer its weight to the ground. During laying, the point where a descending cable first reaches the seabed is called the touchdown point. You find it at the lower bend, where the suspended length makes quiet contact with the sediment and becomes a resting path behind the moving vessel. For a moment, the meeting is visible as a small change in shape. The hanging bend loses height at its lowest part, and the rested section extends away along the floor with no gap beneath it. Fine sediment receives the new weight without a sharp break, leaving only a slight darkening where the strand presses into the surface. The contact does not stay fixed in one place. As the hull advances, the meeting point travels along the surveyed course, with open suspension ahead and settled strand behind. A faint plume rises where the new length presses into the upper grains, then drifts close to the floor and thins. Farther astern, the path lies motionless across the slope, following the direction already chosen. You pass the threshold from descending shelf to the first dark plane. Relief broadens, shadows soften, and the remaining pale tones withdraw from the ground. The coast is now absent from the forward view, replaced by a wide blue-black field whose scale is carried by the small curve of the root and the distant underside of the ship above. For a while, the scene is nearly still. Only the distant hull shadow shifts across the floor, carrying the offshore work onward. Across this flatter region, placement becomes an even repetition of steady movement and settling length. The stern continues along the surveyed direction. The suspended bend keeps its form, and the rested section extends behind over subdued sediment. You do not need a shoreline reference here. Progress appears in the growing distance between the moving hull and the portion already laid across the plain. Once a steady lay is achieved, practical maximum laying speed is about 11 to 15 kilometers per hour, or 6 to 8 knots, with periodic slowing to pass repeaters through the cable handling machinery. The ship's motion, therefore, alternates between sustained advance and measured reductions, visible in the careful passage of a larger component through the equipment before the usual pace returns. Past the stern, the placed length forms its familiar suspended curve and descends toward the plain. Open sea fills the view around the working hull, with no coastal structure remaining near the root. Below, the settled path keeps its restrained direction across gray-black sediment, while the ship carries the next section north into deeper blue. The wake draws a narrow pale seam behind the hull. Beneath it, the laid strand extends across the floor without a surface marker, joining the moving ship to ground already passed. The horizon remains empty, and the offshore course continues with the same measured bearing toward the northern basin. The shelf is now a pale incline behind you rather than the ground immediately below. Ahead, depth gathers under the keel, and the open basin occupies more of the view. The laid strand remains with the mapped course, crossing a surface whose low variations arrive slowly enough to seem almost still. Cold blue above and gray-black sediment below hold the vessel between them. Northward, the route extends beyond the first plane. The near-shore works belong to the connected length astern, while the forward course enters a deeper region without returning to shore. You remain beside the work as the ship carries it onward, horizon empty and the floor beneath growing less distinct in the dark. Farther on, the course will divide into the long dual routes that will reach Svalbard later. For now, that separation belongs to the deeper distance, beyond the shelf and beyond the quiet contact already made with the first plane. The vessel continues north, carrying the strand into colder depth, while the laid path remains behind on the seabed. Beyond the shelf, you pick up the signal where the seabed falls into a broader northern reach. The pulse does not brighten the sea or mark its path on the surface. It moves inside glass, beneath armor and insulation, while the ship's earlier track fades behind. Ahead lies a long run under cold dark, aimed toward the Svalbard archipelago and the settlement of Longyearbyen. The route holds its course without spectacle, passing below swells, wind, and the slow rearrangement of ice farther north. Near the seabed, movement is slower. Fine sediment lifts only when a current reaches low enough to disturb it, then settles again over the armored surface. The path remains where surveyors and the laying ship place it, a narrow engineered trace crossing an immense natural floor. You follow at the pace of transmission rather than the pace of a vessel. A coded burst enters from the mainland, becomes light within the fiber, and travels through a sealed path on the seabed. Above it, the Norwegian Sea opens in wide, nearly featureless distances. The surface may be rough, but the path below remains fixed. Depth increases. Daylight thins into a muted green and then disappears, leaving the route among sediment, rock, and the pressure of the deep. The northward direction is simple, though the ground beneath it is not. Ridges rise and fall. Fine particles gather in hollows. Stones sit where currents have left them, and steep slopes interrupt the otherwise gradual descent. The signal passes through all of it without needing to see the terrain. It keeps to the installed strand, carried from repeater to repeater, while the sea overhead stretches toward latitudes where winter darkness can last for months, and summer light can linger through the night. Pressure increases with depth, closing around the outer sheath from every direction. The glass core remains isolated inside its layered protection, and the information within it continues as timed changes in light. In 2003, Space Norway lays about 400 kilometers of dual fibre-optic cables linking mainland Norway with the Svalbard archipelago. The connection becomes operational in January 2004. The distance is long enough to place the system among major undersea engineering works, yet its purpose is direct: create a dependable high-capacity path between the mainland and the far northern islands. You move along that established route now, not toward a proposed corridor, but through an operating system that has carried traffic for decades. Space Norway describes the Svalbard fiber system as the world's northernmost high-speed connection, designed with 2 two separate cables for redundancy. The pair does not share every risk in exactly the same place. Separation gives the network another path when trouble affects one side. From the surface, there is no sign of this arrangement. There is only open sea, weather, and the quiet geography between Norway and Svalbard. Below, the two routes preserve a practical margin against interruption. Construction of the original Svalbard fiber is completed in 2003 with Tyco Communications, now Subcom, as the contractor. The work joins specialized ships, shore facilities, repeaters, power systems, and carefully prepared landings into one continuous installation. Each part has to meet the same environment in a different form. At sea, the system withstands depth and pressure. Near shore, it meets movement, abrasion, and human activity. At the stations, it becomes equipment racks, feed circuits, optical terminals, and monitored current. North of the mainland shelf, the seabed route settles into the long middle distance. Here, there is little to distinguish one stretch of seabed from the next. The absence of landmarks is part of the setting. A repeater housing appears at intervals, cylindrical and pressure-resistant, then falls behind. Between them, the fiber carries changing patterns of light through a core finer than the outer structure suggests. The large work of connection depends on very small internal dimensions, protected by layers built for tension, corrosion, and time. Steel strength members take the mechanical load. A conductive path carries the electrical feed. Insulation separates these functions from the surrounding sea, while the outer layers absorb the slow contact of sediment and stone. The repeaters are not passive markers. They restore the optical signal so it can continue over the full reach. Each unit draws electrical power sent along the conductive parts of the system. The current must remain stable across a chain that extends far beyond the horizon. At this scale, the route is both optical and electrical. Light carries information, while a carefully controlled feed keeps the undersea amplifiers working. The two functions travel together through the same long, sealed environment. The system voltage is determined by the number of submarine repeaters and the length of the cable. Longer distance needs higher voltage. That relationship is practical rather than abstract. Every repeater adds a load, and every additional reach adds resistance. The feed must overcome both while maintaining the required current through the chain. On a short coastal link, the demand may be modest. On this northbound system, the electrical design has to account for the full span between landing stations. You remain beneath the broad dark sea as the feed holds steady. Voltage is present across the long conductive path, but the operating target is constant current. Each repeater receives what it needs in sequence. A disturbance at one point can affect the whole chain, so the shore equipment is designed with the length of the system in mind. distant ends are not merely places where traffic enters and leaves. They also act as electrical anchors for the submerged equipment between them. To improve reliability, power feeding equipment capable of the full system voltage is installed at landing stations at both ends of the system. Either end, therefore, has the capacity required for the complete undersea span. The arrangement is deliberate. It avoids making one shore terminal the only source able to sustain the repeaters. At the mainland station and at the Svalbard station, the installed feed is sized for the same full demand, even when normal operation shares or assigns the load differently. If power feeding equipment fails at one landing station, the equipment at the opposite station can feed the total system voltage, so constant current continues to the repeaters. The failover crosses the entire submerged reach. One end takes responsibility for the full chain, and the undersea amplifiers remain energized from the surviving station. This is dual-end power failover in plain terms. Either shore can power the whole system when the other shore cannot. Out at sea, the result is uneventful by design. The signal does not pause to announce a change in its source of power. Repeaters continue their work in the dark, each one receiving current through the same conductive path. Above, wind can push long bands of foam across the surface. Farther north, drifting ice can collect in loose fields. None of that reveals which station is feeding the system at a given moment. Reliability appears as continuity, not as display. The route continues toward the high Arctic, though it remains south of the pole and tied firmly to inhabited shores. You pass beneath waters used by fishing vessels, research ships, cargo traffic, and patrols. Then, beneath quieter reaches where traffic thins, sound travels far in the deep. A propeller may be heard long before its hull passes overhead. The installed path stays on the seabed, held by weight, burial in selected areas, and the careful choice of terrain. Sediment softens some sections, allowing the armored path to settle slightly into the bottom. Elsewhere, exposed rock keeps it visible. In steeper ground, route planning matters because gravity, tension, and movement can concentrate stress. The original survey work reduces those risks before installation begins. The operating system carries the memory of those decisions in its curves. Broad changes of direction, gradual crossings, and avoidance of hazards that remain unseen from the surface. As you move north, the seasonal world above changes. In winter, darkness covers the sea for long periods, and storms move through with little daylight to reveal them. In summer, the sun may remain near the horizon, spreading low illumination across fog and open leads in the ice. The system below does not follow those cycles. Its repeaters operate in constant darkness, and its optical traffic moves at the same pace whether the surface is black, silver, or bright with low Arctic sun. The route approaches the Svalbard margin through colder layers and increasingly Arctic conditions. Shelf contours rise from the deep, and the bottom becomes more varied. The islands are still beyond view, but their geology begins to shape the approach. Valleys cut beneath the sea, slopes gather sediment, and glacial history remains in ridges and scoured ground. The signal crosses this older landscape without changing speed, carried toward the landing that connects it with Longyearbyen. Longyearbyen sits beside Adventfjorden, with steep mountains enclosing the settlement and broad slopes marked by snow, scree, and permafrost. The fiber route reaches land within this high-latitude setting and enters shore infrastructure built to protect the transition from sea to station. The optical path leaves the pressure of the seabed and passes into controlled buildings where technicians can monitor transmission, current, and alarms. Outside, the fjord reflects low cloud and the muted colors of Arctic rock. Space Norway says the subsea network is particularly essential for downlink operations at Kongsberg Satellite Station in Longyearbyen, also known as Svalbard Satellite Station, or SvalSat. The connection gives the station a high-capacity route south from its polar location. Data received from spacecraft can enter the terrestrial network without waiting for physical transport or relying only on narrower alternatives. The Undersea system turns a remote receiving site into a connected part of a much larger ground infrastructure. You climb in viewpoint from the shore toward the plateau where the dishes stand. The ground is open, wind-shaped, and sparsely vegetated. Snow gathers in shallow depressions and along the lee side of structures. Each antenna faces a wide portion of sky, ready to track spacecraft that pass over the polar region. Their movement is measured and mechanical. A dish turns, pauses, follows an arc, and returns, while the fiber path below carries away what the antenna receives. The pass may be brief, but the preparation is continuous. Predictions, equipment checks, and scheduled contacts align before the spacecraft rises into view. SvalSat, part of Kongsberg Satellite Services, or KSAT, is described by Space Norway as the world's largest ground station for downloading data from satellites in polar orbits. Its position near the top of the globe gives it frequent access to spacecraft that circle Earth from north to south and south to north. Many such satellites pass within view on each orbit. The quiet field of dishes is therefore not isolated from motion. It is placed where orbital paths repeatedly cross the northern sky. A polar orbiting spacecraft approaches from beyond the horizon, too small to see with the unaided eye. The station predicts its pass precisely. One antenna aligns with the expected track, receives the downlink, and sends the incoming stream into local systems. From there, the data enters the fiber connection, and begins the long southbound transit beneath the sea. The same route you followed north now carries observations away from Svalbard, turning a brief overhead pass into usable information elsewhere. Data distributed from Sat via the fiber connection supports weather forecasting, ship traffic surveillance, environmental monitoring, Arctic ice mapping, and communication during critical phases of rocket launches. Each use begins with a downlink that may last only minutes. The receiving antenna gathers the stream, station equipment checks, and routes it, and the undersea path carries it onward. The applications differ, but they share the need for timely, reliable transfer from this remote northern site. Whether instruments in orbit observe cloud systems, temperature patterns, moisture, and movement across large regions, their passes over the Arctic provide information that can be combined with observations from elsewhere. Ship surveillance uses other spacecraft and sensors to follow activity across northern seas. Environmental monitoring tracks broad changes in land, ocean, and atmosphere. Ice mapping turns repeated views into practical knowledge of where pack ice, leads, and seasonal edges are forming. During a rocket launch, communication through ground stations can matter most during specific parts of ascent and early flight. Svalbard's location makes it useful for contact with trajectories that pass through northern coverage. The dishes do not make the launch visible from the plateau, and the undersea system does not carry flame or sound. It carries telemetry, commands, status, and other signals as structured data, moving through glass while the physical event takes place far away. The station's scale becomes clear not through noise, but through repetition. Dish after dish stands on the plateau, each built around the same need to point accurately and withstand Arctic conditions. Foundations meet permafrost, motors work in cold air. Protective covers, heaters, and maintenance routines keep the antennas available through snow and wind. Beneath them, buried terrestrial fiber gathers the separate receiving systems and directs their traffic toward the shore connection. Longyearbyen remains nearby, a compact settlement between mountain and fjord. Buildings cluster along the valley floor. Roads follow the terrain. Utility corridors, communications equipment, and landing infrastructure tie the community to systems that reach far beyond the archipelago. The dual strands under the sea are one part of that support. They serve everyday communication as well as specialized satellite work, carrying ordinary network traffic beside data gathered from orbit. At the landing station, optical signals are received, checked, and passed into local networks. In the opposite direction, traffic from Svalbard is prepared for the long transit south. The power feed remains part of the same installation, sustaining repeaters far out beneath the sea. Shore equipment and deep-sea equipment operate as one continuous system, though they occupy very different environments. One stands in controlled air behind walls. The other rests under pressure in darkness for years at a time. The system is old enough for its installation history to sit beside its daily operation. Components are monitored for drift, faults, and changes in performance. Marine repairs, when needed, require specialized ships and careful recovery from depth. On shore, modules can be inspected and replaced more directly. The long submerged sections are less accessible, so reliability begins with robust design, duplicated paths, stable power, and continuous observation of small changes before they become larger problems. Around Svalbard, the environment continues to impose its own schedule. Sea ice advances and retreats. Glaciers flow toward fjords. Storms cross the islands. Permafrost holds the ground, though its condition varies with season and long-term warming. The station dishes continue to track overhead passes, and the undersea route continues to carry their data. Technology here does not replace the Arctic setting. It occupies a narrow, maintained place within it. Space Norway gives the Svalbard fiber cables an estimated technical lifespan until the end of 2028. Extended operation beyond 2028 is possible, but not guaranteed. You hold at Longyearbyen with that limit in view. An operating system still carrying current and light, yet approaching the edge of its planned technical life. The plateau dishes remain turned toward polar orbits, and the seabed route remains active below the fjord and the open sea. A later Arctic system is announced beyond this horizon. But here, the older pair continues its work in the cold north. You rise above Longyearbyen without losing sight of it. The settlement draws inward beneath you. A few long roofs, pale roads, dark slopes, and the quiet geometry of buildings gathered near the shore. Beyond them, the valley opens toward the fjord. Snow remains in folds of the mountains, and the higher ground keeps its muted gray. From this distance, the town is not a center so much as a small arrangement held inside a much larger Arctic. You continue upward until roofs become marks, roads become faint threads, and the coast settles into a clear edge beneath a wide, cool sky. From here, the announced Arctic Way system is still an intention described in contracts, routes, and engineering plans. Space Norway has signed a contract with Subcom for full system supply, covering survey, design, manufacturing, and installation, with service scheduled to commence in 2028. Nothing in the dark below needs to be imagined as finished. The work belongs to measured stages. Ships charting the seabed, factories preparing long sections, shore teams planning landings, and engineers fitting each part to conditions that are already well known for cold, distance, and limited access. You move southward in thought while remaining high above the Arctic. The specified form is trunk-end branch, repeatered, with direct shore-end landings at Bodo, Jan Mayen, and Longyearbyen in Svalbard. The trunk carries the main path. A branch reaches aside to an island or coast, separating from the shared path without losing connection to it. Repeaters sit at intervals along the submerged span, restoring optical strength so signals can continue over long distance. The 3 landings give the planned system its practical shape. Mainland Norway in the south, Jan Mayen farther out, and Svalbard in the north. The announced total length is 2,350 kilometers. Seen from above, that distance does not appear as a single gesture. It passes over deep basins, shelves, slopes, and narrow approaches to land. It includes the ordinary precision of choosing where a shore end can arrive, where a path can avoid rough ground, and where each submerged section can be joined to the next. The number is large, but it is also exact enough to become a work plan, divided into survey blocks, manufacturing lengths, installation sequences, and tested sections. The path lies entirely within the Arctic Circle, between 67 and 78 degrees north. In this band, daylight changes greatly through the year. Summer holds brightness for long stretches, while winter keeps the sun low or below the horizon. The planned path remains inside that northern measure from end to end. You can hold the latitudes as 2 quiet boundaries, one near the mainland landing, the other above Svalbard, with the course passing among coasts and islands that share the same broad season of ice, wind, and long changes of light. The 2 existing Svalbard cables do not disappear from the picture. While Arctic Way is being established, Space Norway plans to keep using them as backup for as long as they remain functional. Their presence gives the newer plan continuity rather than replacement in a single moment. The older pair still carries its purpose, while the announced system moves through design, manufacture, and installation. From your distant view, the old and the planned routes belong to different times, yet they overlap in responsibility. One already serving, the other being prepared. Subcom supplied the original Svalbard system and is also the provider for Arctic Way. The earlier connection and the announced one belong to different periods, with different equipment, design choices, and capacity needs. The shared provider brings prior experience with the northern corridor into the newer contract. You remain far above the details. Below, specialized work returns to familiar coasts with updated surveys, manufacturing plans, repeaters, shore ends, and terminal equipment prepared for the requirements of the planned system. Bodo rests on the mainland side of the announced path. From the air, the coast is broken into bays, low islands, and darker ridges farther inland. Jan Mayen stands apart from the mainland and Svalbard, with its high ground rising from a broad emptiness. Longyearbyen remains behind you to the north, close to the head of its fjord. The planned branch structure gathers these different shores into one system without making them alike. Each landing has its own geology, approach, weather, buildings, and access, and each must receive the same careful transition from submerged fiber to equipment on land. A shore end is a place of gradual change. Far offshore, the armored structure is chosen for deep conditions and long unsupported distance. Nearer land, protection increases as the path enters shallower ground. The final approach must fit the slope, the seabed, and the built landing point. On shore, the optical path enters a controlled space where power, monitoring, and terrestrial connections take over. You do not need to descend to see the labor involved. The landing is small against the coast, but it is where the submerged course becomes part of daily infrastructure. Farther out, repeaters divide the long span into manageable optical reaches. They are sealed housings built to remain under pressure for years, passing amplified light onward through paired fibers. Their spacing belongs to the design of the whole system. Too far apart, and the signal weakens beyond the intended margin. Placed correctly, they support stable transmission across the course. Power reaches them through the same long structure that carries the fibers. From above, none of this is visible. The sea surface keeps its plain appearance, while a sequence of engineered points is planned far below. The Arctic Circle is a geographic measure crossing mainland, islands, and open sea. Because the entire passage remains north of it, the plan has a distinct operational setting. Seasonal access, cold weather procedures, survey timing, and shore work must all fit the region. The engineering is patient and specific. Charts are revised, seabed profiles are checked, landing approaches are compared, and the future course becomes clearer through repeated observation and recorded measurements. The contracted work begins with survey, because the planned way must be described in far greater detail than a distant view can show. Depth, slope, sediment, exposed rock, and the approaches to each landing must be recorded and compared. Design follows from those observations. Manufacturing then turns the design into physical sections, repeaters, branching equipment, and shore-end protection. Installation brings those prepared parts into the Arctic in an ordered sequence. Each stage depends on the previous one, and every completed stage must meet the required standard before the next can proceed. The branch toward Jan Mayen gives the planned arrangement a clear structural difference from a simple shore-to-shore span. At the branching point, the optical paths are directed so the island landing joins the main trunk. That point must be treated as part of the full repeater design, not as a separate local addition. From the surface, the island remains a narrow mass against the horizon. Far below, the branch is planned as an integrated part of the same northern system, carrying signals toward shore and back into the shared track. Manufacturing must also match the order in which the system is installed. Long sections are prepared, tested, stored, and loaded so they can leave the vessel in the planned sequence. Repeaters and branching equipment are included at their assigned positions. Near each landing, the construction changes to suit shallower ground and greater exposure. Offshore sections are prepared for long depths and pressure. The completed system is therefore not one uniform object, but a continuous assembly whose protection and equipment vary with place, while the optical strand remains connected. Testing continues before, during, and after installation. Optical measurements check that fibers pass signals as intended. Electrical checks confirm the power corridor for repeaters. At the landings, terminal equipment must recognize the full submerged span and report its condition. These procedures are quiet and repetitive by design. A result is measured, compared with expected limits, and recorded from your high position. The work appears small beside the Arctic coast, yet every reading helps turn an announced approach into an operating system. A planned system also has a long administrative life before it has a physical one. Survey records, run positions, manufacturing logs, test results, and installation plans must remain consistent across many teams. A change in one place can affect work elsewhere, so revisions must be traced and checked. This quiet coordination is part of the engineering. Far above the Arctic, you see only a vessel, a landing building, and a distant coast. But the work also exists in precise records that keep the same course understood from design through commissioning. The completed span will be monitored from shore through optical and electrical measurements. Terminal equipment can compare present readings with expected conditions and help operators identify where attention is needed. The submerged structure itself remains inaccessible during ordinary service, so reliable observation from the landings matters. In the high view, those stations are small silhouettes near the coast. Their equipment rooms hold the active end of a thread that extends far beyond sight, through pressure and cold, toward other shores. You widen the view now, not to leave the Arctic behind, but to place its planned reach beside a few larger systems elsewhere. The comparison is only scale. Different oceans, landing conditions, owners, and purposes produce different designs. Yet the basic task remains recognizable. Carry light through glass across a great submerged distance. Protect it. Power the active equipment where needed, and bring it ashore at prepared sites. The wide ocean does not make these systems abstract. It makes every practical choice more important, from course survey to final testing. MAREA is described by Telxius as a 6,600-kilometer submarine cable with 200 terabits per second of capacity. connecting Virginia Beach in the United States with Soplana in Spain. Its Atlantic span is nearly 3 times the announced length of Arctic Way. The larger number does not diminish the Northern Passage. It simply shows how far an ocean crossing can extend when 2 continental shores form the endpoints from high above the Atlantic. The distance contains changing weather, currents, great depth, and darkness between 2 small landing places. Capacity gives another measure. That figure describes the amount of data the system is designed to carry, not the physical size of the glass itself. Many optical channels travel together, separated by wavelength and managed by equipment at the ends and along the way. To you, the ocean remains unchanged. No brightness rises from below, and no mark appears on the surface. The traffic is carried as modulated light inside fibers, moving through an environment that stays cold, pressurized, and almost entirely unseen. Dunant offers a second scale cousin. Subcom and Google announced it ready for service as the first long-haul subsea cable to use a 12 fiber pair space division multiplexing design, delivering 250 terabits per second across the Atlantic between Virginia Beach and St. Hilaire-de-Riez on the French Atlantic coast. The design increases the number of parallel optical paths within the same broad system. Rather than asking each fiber pair to carry as much as possible on its own, space division multiplexing distributes traffic across more pairs. On Dunant, pump sharing technology allows pump lasers and associated optical components to be shared among multiple fiber pairs, enabling more fibers in the cable. That sharing reduces the need to duplicate every active component for every pair. The result belongs to a careful balance among power, component count, physical space, and capacity. The shared components serve several neighboring optical paths, while the arrangement remains sealed inside specialized repeater equipment far beneath the surface. MIST provides the last brief comparison. NEC identifies it as an 8,100 kilometer cable system connecting Singapore, Malaysia, Myanmar, Thailand, and India through Mumbai and Chennai. Capable of more than 216 terabits per second, using wavelength division multiplexing. Its track crosses a different ocean region and links several shores rather than 2. The larger network shape shows how a long system can gather multiple landings while preserving high capacity across a wide span. Wavelength division multiplexing allows many optical carriers, each using a different wavelength, to travel through the same fiber. At the landing stations, equipment combines them for transmission and separates them for reception. The idea is compact, even when the strand is vast. Many distinct streams share the same glass without becoming the same signal. Across MIST, that method supports the stated capacity through a sequence of national landings. From your high view, the technical density is hidden inside a course that still meets the shore in quiet buildings. The comparisons now recede. MAREA shows a long two-shore Atlantic span. Dunant shows how more fiber pairs and shared pumping support greater parallel capacity. MIST shows a longer multi-landing system using many wavelengths across a broad regional corridor. Each is large in a different way, and each remains only a cousin to the announced northern design. Arctic Way has its own scale, its own branch to Jan Mayen, its own mainland and Svalbard landings, and its own schedule still ahead. As the northern coasts return, the comparison in scale becomes simpler. The Atlantic systems extend between distant continental shores. The Asian system gathers several landings across a much longer regional approach. The Arctic plan remains wholly inside the northern circle. Their capacities and fiber arrangements answer different requirements. Their common work is to preserve optical transmission across distance, protect the fibers, support active equipment, and deliver the signal intact to shore. The oceans differ, but the need for exact survey, manufacture, installation, and testing remains. You turn north again, keeping the perspective wide. Longyearbyen is still far away, and the planned run remains a future arrangement of surveys, manufactured sections, repeaters, branches, and shore ends. Nothing needs to be hurried into the present. The Arctic keeps its distances, and the engineering proceeds by contracts, measurements, seasons, vessels, and tests. Below, the wide ocean begins to narrow into the familiar approaches of the north. Islands grow more distinct. Coasts hold their shape for longer beneath you. The pale horizon closes around the span you have followed from one announced landing to another, then outward across larger systems, and now back toward the Arctic. Home is still ahead, not yet arrived. The view remains open, the shore remains distant, and the dark between them is calm. The farthest northern reach begins to recede. Cold distances lose their sharp edges, and your attention settles on one Pacific coast. You come back toward Oregon, toward a small shore station in Pacific City. Here, 2 cable landings serve important sites of the cabled array, including axial seamount. It is a quiet discovery. 2 arrivals from the sea beside an ordinary town, carrying the work of a distant volcano into rooms on land. You notice it, hold it for a moment, and then continue home. From that station, the system extends outward through about 900 kilometers of modified telecommunications cable. Installed in 2012, it supplies 7 primary nodes on the cabled array. The scale is large, but the arrangement is practical. A long engineered path reaches from the coast to fixed points offshore, where the nodes distribute connection and power to instruments placed in carefully chosen locations. The old purpose of carrying messages has been adapted to support a permanent field of observation. The Ocean Observatory's Initiative cabled array provides 10 kilovolts and 8 kilowatts of power, together with bandwidth, to scientific sensor arrays on the seafloor and through the water column. The current does not simply end at the first junction. It reaches equipment that listens, measures, records, and sends a steady signal back toward shore. Remote instruments remain part of an active observatory rather than isolated objects in the dark, each one connected to an ongoing stream of work on land. OOI describes the cabled array as the first United States ocean observatory to span a tectonic plate. Across the Juan de Fuca plate, near real-time data moves from remote instruments toward researchers on land. You pause only long enough to take in the shape of that achievement. A plate crossed, many sites joined, and events far offshore made present without waiting for a ship to return. The distance remains immense, yet the delay is reduced to something close to the pace of the event itself. At Axial Summit, the connected instruments gather around a remarkable setting. The site is described as the most advanced underwater volcanic observatory in the world's oceans, and it hosts active hydrothermal fields. Heat rises through fractured rock. Mineral-rich flow enters the cold surroundings. Sensors remain nearby, not as visitors passing through, but as patient witnesses to gradual change and sudden activity at the summit of a submarine volcano. Their presence turns a remote summit into a place that can be watched over time. Then you leave the research observatory behind. It remains a cousin to the great communication routes, built from related methods, but serving a different purpose. The same broad skills appear here, laying a durable path, feeding power from land, joining distant equipment, and bringing a signal back. But you do not begin another outward leg. Your way turns inward again, away from the volcano, and toward the practical forms that bring shorter crossings into reach. Some routes do not need repeaters at all. Alcatel Submarine Networks describes unrepeated networks as having no submerged active electronics, specified for distances up to 500 kilometers. The statement is plain and useful. Over a shorter span, the signal can travel without powered amplifying equipment placed beneath the surface. Fewer active components lie offshore, and the route depends on the strength prepared at its ends and the quality of the passive path between them. NEC draws the same distinction by purpose. Repeatered systems are used for transoceanic applications, while repeaterless systems serve shorter routes, such as links from a continent to an island. One form crosses an ocean basin with periodic assistance. The other reaches across a more limited gap. Both begin and end at shore, but their equipment differs according to distance, loss, and the work expected of the connection. The route determines the architecture, and the architecture stays close to the needs of the route. Even a buried route may need to be found again. Power feeding equipment can superimpose an AC low-frequency signal used in submarine cable location search. A search vessel can listen for that added tone and narrow the position below. The locating signal is not the message carried in ordinary service. It is a deliberate marker, applied for the work of finding the route when charts, burial, shifting sediment, or damaged gear make certainty difficult. Before installation, surveys build a careful picture of the path. They record water depth and seabed topography, the type and thickness of sediment, and potential natural or human-made hazards. A smooth-looking stretch may hide steep ground, unstable deposits, rocky outcrops, or places where fishing and anchoring are common. The survey does not make the sea predictable. It gives planners enough detail to choose a safer corridor and prepare the right protection. The same caution continues after the route is placed. In the OSPAR region, about 70% of all cable damage is attributed to fishing and slash or anchoring. The figure turns attention toward busy coastal shelves, where trawls, nets, and heavy anchors may cross the same ground as buried communications. Much of the risk gathers near human activity, not in the deepest quiet, and repair work often begins with understanding what happened on the seabed above the route. With that final measure in mind, you come fully back toward land. The coast is no longer a distant edge. It is close enough for dark pines, wet sand, and the low shapes of buildings behind the dunes. Offshore systems fade from view, though their work continues beneath the surface and under the beach. The technical names loosen their hold. Plate, node, station, field, and signal become parts of one receding scene. You follow the imagined path inland. It passes the shore station, leaves the salt air, and joins the ordinary infrastructure of streets and walls. Nothing announces its arrival with grandeur. The connection simply becomes part of the built world, entering the same quiet geography as utility rooms, corridors, lamps, and sleeping houses. A route that crosses remote ground ends among familiar materials, concrete, timber, glass, and softly lit rooms. The room where you began is waiting. Amber light rests on the floor. The window is dark now, holding only a faint reflection of the interior. Beyond it, the coast lies still. Farther out, nodes and instruments remain in their appointed places, while shorter routes, long crossings, and shore equipment continue their separate tasks. You no longer need to follow every connection. It is enough to know that each has reached its proper end. Beside the bed, a small device keeps its unobtrusive connection. The signal that reaches it has crossed many boundaries without asking for notice. Rock, sediment, beach, conduit, wall. Here, at the end of the long return, the vast system becomes simple again. A dim indicator, a resting screen, a room held in warmth. The distant engineering settles into the background, present, but no longer demanding attention. You let the offshore distances settle into silence. The plate, the volcano, the survey vessel, the buried path, and the shore station no longer need to be held clearly in mind. They recede in order, leaving only the steady nearness of home. The bed supports your weight. The blanket lies smooth beneath your hand. The amber light softens at the edge of the room. Outside, the Pacific coast remains beyond the glass and beyond the sleeping streets. Inside, everything has returned to its proper scale. A bedside connection, a quiet wall, a familiar blanket, and the calm of being ashore. No farther distance asks to be crossed. The room is warm, the device is still, and the night gathers gently around the bed.